Hey team, I'm in 13-5 looking at spheres and hemispheres. So you probably know a sphere is just like a ball shape. The mathematical definition is that it is a solid figure, a round solid figure. It's a 3D figure with every point on its surface being equidistant, equidistant, oh, ran out of space there, equal distance from the center. So it's kind of the same definition as a circle, except we're talking about 3D instead of 2D here. And then hemisphere, you've probably heard this word before, like northern hemisphere, southern hemisphere of the Earth. It's just half of a sphere. Okay. We're mostly going to focus on the volume of these two figures, but I'm also going to show you the surface area because that does come up as well. And I want to try to explain these three formulas because if you just take a look at them, it's not exactly obvious where they come from. There are some familiar components to them, but like if I'm looking at the volume of spheres, like where does that 4/3 come from? Like I don't know. If I'm looking at the surface area of a sphere, like pi r squared, I get that. Like that's the area of a circle, but then where's that 4 come from? Why is it 4? Um, there's a couple different ways to prove these formulas. I'm going to try to show you guys in my crude drawings kind of the most straightforward way to understand them. If you're interested in to learn more about these formulas, I can definitely share some links which use computer-generated images to try to show these a little bit more deeply than I can. But okay, I'll try my best here. Let's start with the surface area of a sphere and this formula right here, 4 pi r squared. Like I said, this pi r squared is familiar to us. Where does that 4 come from? Well, this theorem says, hey, I want to know what the surface area of this, all the parts of the ball that I can see, but that is super difficult because everything's curved, right? It's hard to measure curved things. You can't just put your ruler next to it. So let's say that we turn this into a disco ball type situation because I like the nightlife and I like to boogie on the disco. No, I'm sorry. So we tile this, okay? We tile it all over with these little pieces, and then we project those pieces, whoop, away from the curved surface, whoop, until, let me get rid of this, until we get this more familiar structure, which would be a cylinder. Okay, and it would actually be a cylinder with no top and no bottom, because all those pieces instead have been stacked along the walls of a cylinder, right? So there's no top and no bottom. I'm going to move this down here so we have a little more space to think about it. So I want you to imagine, if you will, we have this cylinder with no top or no bottom, so we really don't care about those pieces. We really just care, if you think about this in terms of like a soup can, we really just care about the label of that soup can. Well, if we only care about the label, then let's just take the label off, right? If you imagine peeling the label off of a canned good, that's actually just a rectangle. So if we want to know the area of a rectangle, that's just good old length times width. So what is this length and what is this width? Okay, well, let's look first at length. And we got to go back whoop, over there. In the context of this, the length is actually just the circumference because we've unpeeled the label, right? So we know the formula for circumference, right? That is just 2 pi r. Okay, that wasn't too bad. How about the width over here? Well, that's actually just the height of the can, which if we go back to our original, all right, all the way back over here, that is actually the same as the height of the entire sphere, which coincidentally is the diameter, and diameters are made up of two radiuses, two radii. So the height is actually two radiuses. So this is going to be 2 radii, which means if we multiply out our rectangle here, we get 4 pi r squared as our area, thus the formula for surface area of a sphere. There are many different ways to explain this, but this I thought was kind of the most easily digestible version. Okay, now volume of a sphere actually comes from the surface area. So let me clean up this that I have here. Whee, boop. All right, so we're going to do the same sort of deal. We're going to tile this, but remember we're talking about volume now. So we actually want what's inside too. So I want to slice out these mini pieces like this, right? So then I got another little tiley piece, and it's going to slice towards the middle, and it's going to slice towards the middle. Whee! And if I pop out these little pieces, what they actually are, right? If this is a little square or rectangular piece, and I'm going towards the center, but it's tapering, it actually ends up being a pyramid. Pyramid. We know the formula for a pyramid, right? The formula for calculating the volume of a pyramid is 1/3 area of the base times height. So if I found the volume of all of these little baby pyramids and added them up, that would be the, sorry, did I say area? If I found the volume of all these little pyramids and added them up, that would be the volume of my sphere. Okay, so can I relate this pyramid to the dimensions of a sphere? Well, for starters, the height of my pyramid is actually the radius of the sphere. So let's just go right ahead and swap out this height for r, because this pyramid actually has a height of r. It's the radius because it's laying down flat like that. I'm going to do a little bit of rearranging here. Woo, boop. And let's put these like so, because I don't actually know how to find the area of one of the base, because I don't know how big I made these little pyramids, right? I don't know how to find the area of the base of one of them. But what I do know is that if I'm going to add up all of them anyway, then I don't need to know the area of one individual base. Why not just say that this is going to be the entire surface area of the sphere, right? Because that's what the area of the base is. It's like all these little tiled disco ball pieces added together. And I have that formula already. So let's plug that in. 1/3 r times the surface area of a sphere, which is 4 pi r squared, which if I do a little bit of rearranging and put the r's together and put the 4 and the 1/3 together, I get 4/3 pi r cubed as the volume of my sphere. Okay, obviously this would be a little bit more seamless if we had a computer generation to computer generator to show us, all these pieces breaking apart, but you can use your imagination a little bit to visualize that. Okay, and then the last formula here, volume of a hemisphere, right? Hemisphere is just half of a sphere, so we basically divide this entire formula in half. So the only thing you're really going to see change is the 4/3 is going to become a 2/3, right? Because it's being cut in half. There you have it.